Okay, yes, let's solve another problem of linear differential equation. Okay, so this is the problem, and in this case we are given an initial condition, which means that we have to calculate the constant. Okay, the first thing to do is to make the shape of the differential equation, of the linear. So we have to make this coefficient 1. The way to do it is to divide by x plus 1 in both sides. Okay, so what is the result is something like this. Derivative y respect to x to the plus 1 over x plus 1 times y equal to the natural log of x over x plus 1. And from here we can check that this is p of x and this is q of x. Okay, now why we need this shape? In order to calculate the integrand factor. The integrand factor is exponential of the integral of p of x, differential of x. Okay, which p of x? This one, right? So that is why we need the coefficient 1. Okay, so it's going to be the exponential of the integral of p of x. P of x is just 1 over x plus 1, differential of x. The result of this integral is obviously the natural log of x plus 1. And here we can see that we can eliminate the exponential and natural log, so the result is just x plus 1. Alright, so what should we do with this w of x? We multiply times the differential equation, and then we can apply the dead step. Well, if we multiply that times the differential equation, is going to be x plus 1 times derivative y respect to x. Now that times this, we can see that the x plus 1 cancels. So it's going to be plus y equal to, here x plus 1 cancels with this, is just the natural log of x. And you can see that we have go back to the original differential equation. But now, what is the difference now? The difference is that we know that we can apply the dead step here. The step. How can we apply the dead step? It's just the derivative of a multiplication. What multiplication? Derivative respect to x of what multiplication? This x plus 1 times this without the derivative, meaning just the y. And that equal to the natural log of x. So what we have done is to replace this by only this. Now checking if it is correct, we have to do this. Derivative of a multiplication is the first times derivative of the second one, which is here, plus y derivative of this, which is just 1. So it is correct, alright? Okay, so that is the dead step. Then, now it is a variable separable differential equation here. Variable separable differential equation. And we can solve it by separating the differentials. Okay, so differential of x plus 1 times y equal to the natural log of x, differential of x, and it is separated. Now, you may wonder, it is not variable separable because I have here x and y. You are right. Here we only have x, and here we have x and y. But why it is variable separable? Because of these engineers. This is considered a single variable because this and this cancels. Alright? Just like when you have the integral of the differential of x, it cancels, it's just x. Or the integral of the differential of zeta, is zeta because it cancels. So here it is considered a complete variable separated from this variable, and we can cancel it. If we don't have this, then we apply the previous rule where we don't have the separated variables. But here it is an exception, alright? Okay, let's continue. If we cancel this, then this is going to be x plus 1 times y equal to the integral of the natural log of x, differential of x. We can apply integration by parts, or we can use the table of integrals, which I have it here, okay? The integral of the natural log of x is just x, the natural log of x, minus x, plus a constant, okay? Now let's clear the y. Clearing the y is going to be y equal to the x natural logarithm of x minus x over x plus 1 plus, remember that this is going to divide this number, but also divides the constant over x plus 1. I usually separate this to just to remark that this is one part of the solution, which is called the homogeneous solution. Homogeneous. Alright? And this is another part of the solution, which is the particular solution. You don't have to note that in the homework or in the examination. It's just that we are going to use this concept later. Particular solution. We are going to use this concept in second unit. Okay. Okay, now are we done? Probably. Here we have the explicit solution, but it is going to be this family of solutions because we are given an initial condition, then we have to calculate the constant. Remember that in linear differential equation you always get the explicit solution. Alright? Okay, now let's find the value of the constant. The value of the constant is with x equal to 1 and y equal to 10. So let's calculate that. So we replace the value of 10 in y equal to x1, the natural logarithm of 1, minus 1 over 1 plus 1, Papi, plus the constant over 1 plus 1. Okay. Okay, now the natural logarithm of 1 is equal to 0. So this is going to be 10 equal to, okay, be careful here, minus 1 over 2 plus c over 2. Let's multiply times 2. So this becomes 20 equal to minus 1 plus the constant. So the value of the constant is equal to 21. Okay, so now let's write the specific solution. The specific solution then is equal to x, the natural logarithm of x minus x over x plus 1 plus 21 over x plus 1, and this is the solution. Alright? Okay, with these two examples of solving linear differential equations, I think it's enough for you to start doing the homework and to start practicing the linear differential equation. Again, the most difficult part and confusing part is the step. How can you get from here to here? Many students ask, where was left this y? Okay, I suggest you to check the videos and see how this vanished from here to here. All right? In reality, it doesn't vanish. It's not black magic. It was being proved that we can change from here to here. Okay, see you in the next video.